I'm going to talk about the Aditya-L1 mission. It's basically a mission to observe the sun from space. The background picture actually clearly spells out what is the objective of the Aditya-L1. I'll go a bit more detail on the background picture in subsequent slides. What you see here is the sun, which is marked as a orange ball in this picture, and we are here on the Earth. And the L1 point, the Lagrangian point of Sun Earth, is situated somewhere around 1% of the distance from the Sun to the Earth. So that is marked here. And what you see here in this picture is the dynamical events which we see it on the Sun. The bright yellowish structure, what you see here is so-called solar flares. And the big part of the structure, what you see here is the coronal mass ejections, which are the mass which it gets ejected from the sun and travels in the interplanetary medium. The space between the sun and other planets, we call that as an interplanetary medium. And the grayscales, what you see here is nothing but your magnetic fields from the sun, and they are like a turn and twisted because of the rotation of the sun. So if you have a magnetic bar and if you start rotating it, depending on the differential rotation, the magnetic field lines gets curved like a ballerina skirt. We call that as a Parker's spiral. That is, these field lines are spiraled because of the rotation of the sun. And these coronal mass ejections are the solar wind, which is coming from the sun. I mean, sun emits the particles continuously. We call them as a solar wind, apart from these coronal mass ejections. Since they are all charged particles, that sun is nothing but a gas ball of plasma. Plasma is nothing but a sum of positive and negative ions, and electrons and protons. So what happens is, since the ions or the charged particles cannot cross the magnetic field lines, they tag along the magnetic field lines and propagate in the interplanetary medium. So the yellowish thing, what you see here, is nothing but the particles getting tagged along the magnetic field lines and then propagating in the interplanetary medium. They make a curvy structure. Is nothing but your well-known Lorentz force, which you have studied in your schools or college textbooks. That when you charge particles having a velocity and crossing a magnetic field at an angle, will start to spiral along the magnetic field lines at certain radius of curvature, which is called as the Darboux frequencies, and that is what we see here as a yellowish structure. But you also see a structure we call that as a shock. This shock is created because when the coronal mass ejections are ejected from the sun, it is ejected at a speed much faster than the speed of the solar wind, which is going through the interplanetary medium in a continuous manner. So when a bus is moving in the road, and suddenly when you have a very fast moving bus which is coming forward and then moving towards it, you always get a shock trend, which is the shock which you see here. And this shock can accelerate the particles. So the particles which get accelerated from the sun due to solar flare or coronal mass ejections, they get further accelerated by this shock before it travels in the interplanetary medium. And you can also see that the magnetic fields have a path to come to the Earth. So the particles what you receive at L1 need not come from the line of sight of the place, but it can be coming from a totally different position on the sun. So measuring the magnetic fields at L1 and its direction is important to know from where this particle is coming from for you to understand the source regions of the system. Okay. Now, this whole process of solar flares and coronal mass ejections are the reason for what we call it as a space weather, which do affect the planets, especially Earth, as well as other planets also. The source of this emission is from the sun, or it can be from the galactic cosmic rays. I mean, of course, our solar system is mostly affected by the sun. And the distance between the sun and the Earth, or even up to something like Jupiter, we call that as a inner heliosphere. and outside of that distance we call it as an outer heliosphere. So that is where the heliospheric concept comes in the solar system. And so what are the sources which we already discussed? The solar wind, which is a continuous flow of charged particles from the sun, which permeates the solar system. The coronal mass ejections, which also we discussed, significant release of plasma and associated magnetic field from the solar corona. And we also have flares, which is the sudden release of energy in the form of high energy radiation. And the CIRS, which is the interaction regions between fast and slow solar wind that rotates with the sun, which is also indicated as a kind of a shock front where you have a fast and slow plasma which is following, which is flowing from the sun to the earth. The GCRs are referred to as highly energetic atomic nucleus or other particles traveling through the space at a speed approaching that of light. So they can also cause the space weather effects on our planetary system. So keep this in mind when we go and talk about what Aditya is going to do. Okay. Now to do this, to study this phenomenon, we need to have certain measurements. So here are a few examples of what kind of measurements which are needed. If you are going to measure the particles, for example, the particles which is coming from the sun and tagging along the magnetic field lines, if you are to measure them, they all consist of electrons, protons, heavier nuclei, and the GCRs, galactic cosmic rays, which we talked about. And they also have neutrals. That means they also have not so charged particles. Okay. Specifically hydrogen, because hydrogen is the element which is present in the universe abundantly. Okay, so you need to have instruments to measure these for the particles measurements, which is usually in situ. That because you are actually sampling the particles which is passing by the spacecraft where you are measuring it from. And there is another radiation kind of measurements which you can do is the radiation, which is typically the electromagnetic radiations which we receive from the sun and other system, which are nothing but the photons. Then if you want to study the photons, you do the photometry. Photometry is nothing but the flux of photons at a broad wavelength band. And spectroscopy is nothing but the flux of photons at very specific wavelength, addressing the composition of the plasma. And polarimetry is a technique which is used to study how the photons are polarized based on the physical mechanisms which is happening on the sun. So these three are the techniques which are used. And the typical instruments used focus mostly for heliospheric measurements are listed here. For remote sensing, you have images, Doppler graphs, vector magnetograph to measure the magnetic fields, coronagraphs, and the heliospheric images. So these are all mostly for sun, used for other objects as well, like planets, moon, etc. And for in situ, you have electrostatic analyzers, charged particle and ion spectrometers and magnetometers, neutral monitors, including energetic neutral atom analyzers. They are all local measurements, that's why it's called in situ. The specifications vary depending on the location. So if I have to do these measurements near to the Earth, within the Earth's magnetosphere, then the energetic range of energies are different from when you want to observe from outside of the Earth's magnetosphere. The ones which are marked as red here are the instruments which are carried on the Aditya-L1 spacecraft. Okay, this is a movie I just want to show you in the PowerPoint mode. Go to science or run it. What it shows you how the disturbances are propagating from the sun to Earth. These are the disturbances of the electrons, which is propagating from the sun to the Earth. And these are all obtained from our own facility called Umuti radiatoroscope, situated in Umuti, which looks at the scintillation from the sources. And as the electron passes by in the line of sight, the scintillation tells you about density perturbations in the interplanetary medium along the line of sight. From there, you create a tomographic map, and that's how it shows up. So it clearly shows that sun provides a lot of disturbances in the sun-Earth line, which also affects our own planet. Coming back to the slide. moving forward. So we'll come to the Aditya. Aditya, as I said, is going to sample having 4 remote sensing payload, a chronograph, an imaging payload of the images of the solar photosphere and chromosphere, and an X-ray spectroscopy covered where large energy range with the solar and helios, which basically covers the flares and coronal mass ejections as well as the solar wind parameters. And we have in situ payloads, which is 3 numbers: the PAPA aspects and magnetometer. The PAPA, which is a particle analyzer package for Aditya, looks at the electrons which is coming from the sun at L1 points, along with the ions which is coming from the sun. Aspects Aditya solar wind particle experiments looks at the solar wind, especially protons and ions, and the magnetometer looks at the magnetic field at the L1 point. So you do get the particle information, electron, protons, and heavy ions, as well as the local magnetic field. You do get how the CMEs, you do get how the solar flares are happening on the sun, and you also get how the solar wind is probably in the interplanetary. So all these 4 plus 3 instruments together will start to look at the connection between the sun and the interplanetary medium. That is what this Aditya is going to carry forward. Okay, I will not go into the details of this. This is basically linking the solar flares and CMEs, which connect, which is originated because of the magnetic reconnection. The magnetic field plays a major role in doing this particle accelerations as well as the coronal mass ejections. So this will be manifested as flares and coronal mass ejections, which can be studied using SUIT as well as X-ray payloads as well as the VELC. And the accelerated particles in the interplanetary medium, as it reaches the L1 point here, you start to measure the particle as well as the magnetic field measurements. And of course, we can use many of the ground-based radio observations to study the propagations of these particles in the interplanetary medium, as well as the ground-based magnetometer to study how these particles and. So the top of the deck is the coronagraph, and on the side, the green point is the ultraviolet imaging telescope. So these two looks at the solar surface, atmosphere, and the high energy L1 orbiting spectrometer, which is sitting below these packages inside this for what you call the intermediate deck, which will look at the sun as a star hard X-ray photons. And this mobile tower contains the Aditya solar wind particle experiment, which looks at the protons and the heavier ions from the sun. And the other instruments, the SOLEX, which is hiding below the SUIT instrument, will look at the low energy X-ray photons, and the PAPA instrument looks at the electrons and the ions, and the magnetometer, which is right now in the stored conditions, will look at the local magnetic field. Once it deploys into 3 meter and 6 meter 2 detectors, which will measure the 3-axis magnetic field from the at the in situ observations. So I just go through some of the preliminary observations and tell you what its capabilities are. This is about the SUIT instrument, which you can see. It's a filter-based imaging instrument. It has 11 filter, which can be near simultaneously observed. It has 1 detector with 11 filters, so the filter will move the different filters in the field of view and obtain the images in that particular filters. So this is the telescope, and on top of that, what you see here is the radiator plate to cool the detectors to a very low temperatures to get a very good signal to noise ratio of the system. These are the list of filters which is available on in the SUIT instrument. You can see that each of the filters looks at the different regions. For example, this filter looks at the photosphere, and this set of filters will look at the specific line which forms in the chromosphere, and these 2 filters will look at the photosphere, especially for sunspot. And this is the calcium 2K images, which is looking at the chromosphere, and this is the continuous movement. So SUIT will look at the photosphere and chromospheric images And while the VLC, we look at the coronal images. So you get a full solar atmosphere from Aditya-L1. Here is an example image from one of the filters of SOOT. What you clearly see is the dark patches, which is nothing but the sunspot. And then the surrounding dark patches is the bright ones, which are called as flages. And the quiet regions, which are not really quiet, is considered as quiet sun. So we do see all kinds of features on the solar surface. And this is the chromospheric regions of the sun. Here is an example of a zoo of filter images from the SOOT, which covers both chromosphere, which you can see here, and the photosphere structures. What you see here is pretty good sunspot, and the flages which you see in the chromosphere, and the quiet range regions, which you see is really quiet in this particular image. SOOT also has a provision to do a field of view images. So from the full disk image, if I identify that I want to look at only a particular region and want to do a very high cadence observations, for example, in this particular observations carried out on January 24, 2024, we have taken a small regions from the sun and looked at the bipolar structures, sunspot, what you see here. And this can run through all the filters in a much higher cadence compared to when you do a full disk images. So if anybody wants to run a high cadence images, you should go to the field of view mode, select the region of interest, and then go for a high cadence observations. And SOOT can also do a limb observations. What you see here is a small prominences which stands out at the limb. And this particular prominences will also be having velocities and other dynamics. And running through a small field of view in the limb will provide the dynamics of these prominences in a much better, faster sense. And the SOOT did observe a flare. I mean, of course, I don't have a movie for this, but what you see here is a brightened region here is nothing but a flare which has happened on December 31st, just before the New Year Eve flare, which has been observed by SOOT and other instrument on board the L1. Coming to SOLEX, SOLEX is a sun-as star soft X-ray spectrometer, which was put into operations somewhere on 13th of December 2023. As soon as we switched on the payload, we started to see the solar flares light curves. You can see what you see here is the counts, the number of photons which the instrument receives as a function of time. And you can see that there is a lot of variations in the number of photons what you receive. And this bright increase in the counts is nothing but the increase in the energetics which is happening on the sun, which is related to the solar flares. And as you know that the solar flares are classified into multiple domains depending on the energetics, starting from all the way from A class, B class, C class, N class, and X class flare. And you can see on that day, December 14, we have got 2 M class flares and 1 X class flare. So this was the first biggest X class flare of 2023, which is caught by the SOLEX instrument on board Aditya-L1. The advantage of SOLEX is it also does a spectroscopy, and what you see here is the spectra. The x-axis is the energy, y-axis is the counts, and you can see that the spectra and the red line is the physical model fitting of the spectra, which tells us about the plasma parameters of that at that particular time. So we can actually pick up the time duration and get the spectra and fit the spectra and derive the plasma parameters. We get temperature, emission measure, and abundances of these elements. For example, what you see here is an iron. The content of iron in the solar plasma is estimated, and you have calcium, argon, and the iron nickel complex here at this particular region. So we do get abundances of these elements from the solar system. While SOLEX does from 1 to 20 keV, Helios, which is a high energy, covers from 8 to 200 keV. So we do have 2 instruments. Combine them, you get the energetic events all the way from 1 keV to 200 keV. We used to have a mission called RESI, which was a defunct somewhere around 2016 or so, and until now we don't have a continuous measuring instrument to cover the large energy range. Solex and Helios will cover that particular aspect of it. Here is an example of the light curve. Again, same December 14th flare. You can see how different Solex and Helios will look at differently. The blue curve is the Solex curve from 1 to 22 keV, and the green curve is the 6 to 30 keV from the Helios, and the 30 to 150 keV is the red curve. You can see that the light curves are totally different once you go to higher and higher energies. And you can also see that there's a rapid oscillations which happens just before the main flare, which has happened on that particular day. So these all do have a lot of interesting physics behind it, and there is a lot of work which is being carried out by the science team to bring out the physics behind the plasma mechanisms, which is a coupling of plasma and magnetic field, which is going on currently. Here is another flare observed by Helios on February 22 to 2014. Again, what you see is here is the light curve is for different energy band, and as you go to higher and higher energy, you start to see very fine structures in the light curve, which basically tells you about the fine physics which is going on in this magnetically connected solar flare physics. Then coming to the in situ payloads, this is an aspect payload which you saw it in the mounted on the tower on the satellite. This is a tower where two of the systems are mounted. This is the switch package, which is mounted on two orthogonal directions, so that it samples the particles in the ecliptic plane as well as in the perpendicular to the ecliptic plane. So you get a full three-dimensional coverage of how the particles are around the L1 point. So this also has a high energy detectors, which goes from 20 keV per nucleon. That means if you're looking at proton energy of 20 keV to 5 MeV is something which it can do. If it is a helium, which is 2, which will go from 10 keV to 2.5 MeV. It also is mounted at 6 different directions. Again, you want to sample them at different orientations, so that if there is an anisotropy in the L1 point, you'll be able to measure them, which is a unique features of this particular instrument for Aditya-L1. Here is an example of an event which happened in November 2025. You can see that there was a CME which is crossing at around November 2026 at the L1 point. So this is from our own instrument, Swiss instrument on board Aditya-L1. This is from wind instrument on board both energetic events as well as the background events, which is an important element for us to constrain the energy of these particles, which Swiss will be able to do much better than wind instruments. Here is some example of the December 14th flare from the STEPS instrument, which is the high energy protons and high energy helium instrument. And these different curves represents different orientation, and it shows that definitely this is a kind of a isotropic event which all the directors have seen the event. However, there are some differences between each of the directions, which will tell us about the energetics of these events and which direction the source regions of this particular flare will also be will be able to estimate from these measurements. The PAPA instrument, which was switched on December 11, 2023, will measure the electrons and the ions, heavier ions. Here is an example of a December 15th event, again that flare event, which also had a CME. What the top curve shows the electrons, or at somewhere around December 15th. You can see that the enhancement of the electrons as well as the ions around that particular period when the electrons and ions started crossing the L1 point. Here is a measurements of the magnetic field from NOVA satellite. You can see that these particles do carry the magnetic fields along with them, which is an important element for space weather phenomenon. Then coming to magnetometer, I mean, as it is shown in October 16, 2023, And I'm going to show you some measurements which is in the stowed condition. The open condition, the calibrations are going on. We'll be able to get a better results, better accuracies in the unstowed condition. So this is a stowed condition. What you see here is the red curves is from the Aditya-L1, and the blue curve is from the Discover instrument, which is also at the L1 point. You can see that both of them are matching pretty well. This is the Bx component because magnetic fields is a vector quantity which will have three directions: Bx, By, and Bz. So this is Bx, this is By, and you can see that they are matching pretty well. And this is the Bz component. So all three components are measured from the magnetometer in situ magnetometer, which will give us both particle. So that means you have both particles and the magnetic field measurements from the in situ measurements. One of the biggest instrument on board Aditya-L1 is the chronograph. This was also switched on. All 4 channel directors are working fine. Health is normal. However, we are yet to optimize the system for the chronographic measurements. That is currently ongoing. So I'm not going to present any results from BESC for this particular discussion. Now, if you ask me what is the uniqueness of Aditya-L1 compared to any other mission, this is something which we put it down in our project document, that these are the unique points of Aditya-L1, including looking at the CME is very close to the disk, the chronomagnetic field measurements over the active regions, spatially resolved solar disk observations in the near UV, providing information about solar irradiance variations in this particular band, and then the onboard intelligence to detect CMEs and flares and go into a high cadence mode and obtain a good data volume optimization. Flare observations of all flares without any break or sensitivity change. Solar wind electrons, protons, and alpha particles fluxes with direction information. And we also have identified flags which can provide information in advance for space weather events. Out of these all objectives, the 3 of them is already established, and the performance are nominal. The rest of the 4 performance verification is currently ongoing for us to ensure that all provided objectives are met in Aditya-L1. And for you, how you can play a role? We have an Aditya-L1 support cell. The support cell will provide it will be a conducive between the users of Aditya-L1 and payload and science team of Aditya-L1. That means if you are interested in using the Aditya-L1 through your proposal system, and if you want to specifically observe from Aditya-L1, my suggestion is for you to go and approach the support cell. And they also organize training program for users to account with Aditya-L1 proposal processing system and also the data processing. We do have simulated data, right? So we do have a payload verification data, which we use it to train many of the users who can then use the actual data from the Aditya-L1 from their observations for their science. And they are the focal point for clarifications or any queries from the users related to proposal submission form and the data related queries. And they also play a major role in science support for the payload proposal processing system in close collaboration with the payload operation centers. And they also can provide higher level data products, which is an interface of multi-payload data products, which can be carried out, which can be used by the solar community. And this is done with the close collaborations of the POCs. And they also do specific support required, which are relevant for general science outcome of Aditya-L1, but not in the scope of the payload operation center. So these are the mandate of the Aditya-L1 support cell. So I would urge you to search on the internet Aditya-L1 support cell. There is going to be a meeting of this support cell, which is going to happen from end of this month, where some of these trainings are going to be put in for the students, for them to enable to utilize the Aditya-L1 data for their own scientific purposes. So I urge you to look at this Aditya-L1 support cell in the website and try to see whether you are eligible to attend this particular meeting, which would happen by end of this particular month. I think that's all I have, and I'll be happy to answer any questions or clarifications. Thank you very much.